Welcome everybody. Today we're thinking about taking this bungee cord from its equilibrium position and stretching it, and we're going to approach this problem from the perspective of energy. When I'm solving problems with energy, I almost always want to think about using the work-energy theorem, which says the total change in a system's energy is equal to the net work done by external forces. I'm going to pick a system that consists just of the bungee cord today, which means the two external forces I'm dealing with are the forces by my hands on the bungee cord. In each instance, that force is associated with a displacement in the same direction as the force, which means I'm going to get some positive external work done on the system by my hands. And then I can think about where is that energy going? Well, it could be kinetic energy or potential energy that we get out of this. And I can go back to the system to think about why it might be one form of energy over the other. So for kinetic energy, I'm starting the system at rest. There is some movement in the system, but by the time I get to the end, the system is back to rest. So I think I can safely say that there's no kinetic energy change in this system, which means all of the change in energy must be internal potential energy. Now to think about that, I'm not even going to take any strong steps here to do something like model the bungee cord as a spring. I just want to think in the abstract about how I might figure out what this change in potential energy is. And to do that, I'm actually going to rely on this equation right here and my understanding of what's going on. And the way that I'm going to do that is, number one, I'm going to make an assumption that the force that I have to act on the bungee cord is the same as the force that the bungee cord is acting on me. I mean, that's a very safe assumption because it's rooted in Newton's third law about action-reaction pairs. Once I know that, I'm going to make the further assumption that the force that the bungee cord provides is a conservative force, which is a special kind of force that you might learn about in your math class, that for the physics point of view essentially means number one, that we're going to be able to associate a change in potential energy with that force. And number two, that we can only do that, we can only call a force conservative if the work that is done is independent of the path that we take, which means for the bungee cord, for example, if I try to do something like I pull the bungee cord slowly to get to a new configuration, or if I pull it a whole bunch and then relax it, that the work done in those paths and any other path that I might take should be the same. So under that assumption, we can say that the work done by the external forces is actually going to be opposite the work done by the internal force. So rather than try to model the force that my hands have to act on the bungee cord, I'm going to try to model the internal force that the bungee cord is acting back on my hands, and then throw a negative sign on it, which is the same as the negative sign that you're used to seeing in Newton's third law. And now, pulling these two parts of the equation aside, I have a general expression for the change in potential energy due to a conservative force, which is the negative of the internal work done by that